remember we have an exam on Thursday covering material up to what we did last Thursday, which is hashing. So any of the material up to hashing is fair game. What we'll cover today on pointers is not fair game. You will have a one-page, you are allowed a one-page cheat sheet, front and back. And I am thinking of giving you all the option of either doing it on paper or on Blackboard. So I'd kind of like to show of hands to see who might be interested. Well, before I do that, let me tell you what are the pros of doing it on Blackboard. So you would not be allowed to use the computer to do compiling or anything. The entire time you would have to have the whole the browser window would have to cover the entire screen. You would only be allowed to be at the Blackboard site. You could not go to any other site. If you did, you'll get an F in the course. Okay, it's that simple. It's cheating. But the advantage is you can use the keyboard. Some of you are faster keyboardists. It's maybe easier for you to edit code when you're typing in stuff rather than having to write it on a piece of paper. You would still get the paper exam, so you'd still be able to flip back and forth. So the questions would both be on the Blackboard exam and on the paper exam, but you would answer the questions in Blackboard. Okay? If for some reason your internet connection failed and we couldn't quickly get it restarted, you could fall back to the paper exam to finish the exam. Okay? Blackboard would save whatever work you'd already done. So the question is, how many of you would be interested in doing it on Blackboard? Okay, a number of you. So I will try to get both a paper version and a Blackboard version. Obviously, that means you must bring your laptop. Okay. The second fairly obvious thing is make sure it has enough juice to last an hour and 15 minutes. Okay, but like I said, if for some reason it fails, you'll be able to revert to the paper version. Yes, Scott?
Our one-page cheat sheet, can it be anything we want? We can type it out?
Yes, anything can be on your cheat sheet. You can type it out. You can put it in 8-point font if you can read it that low, but you can't bring a magnifying glass, okay? So that's other questions. It looks like it's a 9-question exam. Okay, at this point, I think I have the questions roughed out. It looks like a 9-question exam. There's a little bit of code reading in it. There is some, so your debugging skills get tested, your tracing skills get tested. You write some code fragments. There are some basic, shorter questions covering just certain limited targeted areas. So it kind of covers both specific concepts, targets writing, solving certain problems, although we've typically gone over those types of problems in labs or in class. So it's a mix of some short programming, some code reading. I think there's one essay, and then a couple how do you do this kind of thing. Okay? So other questions? Okay. So today we're going to go into pointers, and we're actually going to continue pointers next Tuesday after the exam. So it's kind of a split thing. And pointers give students a great deal of difficulty. It's a very tough concept to grasp, but it's an important one. And as Dr. Plank says in his notes, the C++ template library tends to mask the need to use pointers, but the standard template library is using them a lot, and you need to be able to use pointers in order to write efficient programs in C++. I find that when I present pointers, two things. First of all, it's good to have alternative approaches. So while I will weave in and out of Dr. Plank's notes on this. I will be doing some of my own way of presenting pointers, as well as showing you his way of doing it. The second thing is, I think the only way you really get it is if you do some work yourself. So for example, after we get through the initial presentation today, you're going to be doing one of the questions on Dr. Planck's 2014 midterm that I told you you couldn't do. But after I get through the introduction, hopefully you will. So it'll kind of be, I'll do a little presentation, then you're going to do a little pointer work, then a little more presentation, then a little more pointer work. So, and you'll have to probably do, this you'll have to do on paper. You can't really do it on a computer. So kind of to motivate it, think about the fact that with vectors, you're able to resize vectors, right? And you're able to dynamically increase or decrease the size of a vector. Okay? Well, did you ever think about how that's possible? How it's able to magically increase the size of that vector? Somehow, when it does it, it's actually having to get access to additional memory. Okay, and you may never have really thought about how the implementers get access to that additional memory, but they have to have a way of doing it. Well, it turns out that if you could look into the standard template implementation for a vector, you would almost certainly find that it's making use of this notion of a pointer. Okay? So let's just kind of get to it, and as we go along we can talk about then what some of the uses of a pointers are. So a pointer is an address. It's a pointer to a piece of memory. Okay? So if I have int, say, A, then we have the stack that you've seen. Okay? And A has a location on that stack. Maybe it's at 1000. Then what we could do, let's say we say int star B. Okay? And B is going to get put at 0 hex 1004. When you put an asterisk in front of a variable, it turns it into what we call a pointer variable. So we say that B is a pointer to a integer variable. So it points to an integer variable. So it's going to have the address of a integer variable. So now let's say that we have A equals 10. Then 10 gets stored with A. Now how do we assign a value to B? The way we assign a value to B is by taking the address of a piece of memory. And one way to get an address is with the ampersand operator. So if you put the ampersand operator in front of a variable, C++ returns the address, the memory address of that variable. So in this case, the memory address of A is what? Based on what you see up there. It's 1000. So what's assigned to B is 0x1000. Okay? Now, what's the use of this pointer? Well, we say that B is now an alias for A. Okay, so B is now an alias for A. So you'll often hear the word alias used. And you might say, okay, it's an alias. How can we assign a value to it? Well, if it's an alias, what can we do with it? Well, one thing we can do is, let's say we do this. We say asterisk B equals 20. Okay? What this does is, this is different. See, here we said B equals. Here we're saying asterisk B equals. So when we just say B equals, we're assigning an address to B. When we say asterisk B, we're saying we're assigning a value to the variable that B points to. Okay, so this is saying assign a value to the variable to which B points. Okay, this is often called dereferencing B. Okay, so you'll often hear the asterisk operator referred to as the dereferencing operator. Okay, so the ampersand, you'll often hear that referred to as the address operator because it takes the address of a variable. And you will often hear the asterisk referred to as the dereferencing operator. Okay, so when you see the dereferencing operator, you're actually making an access to the variable to which that pointer variable points. So when C++ sees the asterisk, it says, I need to go and look at B's address, which is 0x1000, and I need to put 20 into that location. So it ends up changing the value of A. That's why we say B is an alias for A. It's as though we said B is equal to A. Now, would I do something this silly in practice? No. We're just getting started with pointers, so I'm just trying to show you the basics of pointers right now. If this was the only reason for introducing pointers, it would be silly and not useful. But we use pointers for purposes kind of much bigger than this. But we're just getting you used to this notion. Okay? So we have B is, or now we have A is 20. So if we printed out A would print out as 20. Okay, if we printed B, if we printed it properly, we would get a hexadecimal address for B, 0x1000. Okay? And you can also do things, let's say we had int C here. So let's say we have C, it's 0x1008. Let's say we now say C equals B, so we can put B on the other side and dereference it. Again, it says go to the address to which B points, which is 0x1000, and the value at that location is 20, so C gets 20. Okay, now I promised I would go in and out of Dr. Planck's notes, so let me show you Dr. Planck's equivalent, how he showed it in his notes. Okay, so in his notes, he encouraged you to think of pointers as arrows. Okay, I really don't care which way you think of it, but I do think you have to be familiar with both ways of thinking, and also the way I just showed you is the way it's actually laid out in memory. Now the other way to think of it is using boxes, which is what Dr. Planck did. So he had A, and then he had B, and we have C. So when A got 10, A was assigned 10. When B got the address of A, he showed it as a pointer. Okay? Now when you dereference B and assign 20, A gets 20. When you assign C asterisk B, it gets whatever B points to. B points to A, so you get the value of 20. Okay, so you can think of it either way. Okay, but this is the essence of the way pointers work. So questions about that? Any questions? Okay, if that's what I'd like you to do then is see if you can't solve, take a moment, and you may have to, you can also get this by going to Dr. Planck's. I can't quite get this all out here. But this is also in Dr. Planck's 2014 exam. So if you go to, just a moment, if you go to exams, you go to spring 2014 midterm, you go to the exam PDF, and you go to question 8, you'll see the same thing. So take a few minutes. Feel free to work on this with a partner. The only thing missing there at the bottom, if you don't have access to Dr. Planck's, actually, let's see, I may be able to zoom this in. There we go. Now it's all there. Okay. So see if you can't figure out what ends up getting printed out by these statements. You're definitely going to have to probably use some paper and pencil here and do some tracing. So I'm going to give you about maybe I'm going to give you 7 minutes to 10:07. You can code it up. I know you can. That would be absolutely useless, though. I mean, it won't give you any insight into what's happening. Okay, if you have questions and don't know what's going on, please raise your hand and ask for help, because I can explain it more one-on-one, and so can Alan. Like I say, if you're having an issue right here, please raise your hand.
So when you view it, there's
Oh, sorry. Only do the top. I just realized I can't do this bottom. The bottom half is not doable. Only do the top half. Thank you. We haven't gotten to the bottom half. Sorry. Don't do the bottom half. You don't know what new int yet means. Sorry. That's the next thing. Thank you. Only do the top half until you get to c equals new int.
Oh, it's just equal to the memory. Yeah, it's dereferencing D, dereference gives you the value there.
No, B is not the point of this. B is whatever is C. B is not a point of this. B is. Doesn't make. Doesn't want
It's not. Yep. Right, but we have to explain that. Kind of haven't. There's a little more to it than just that. Okay, let's hear a little buzz. So let's go over what's happening here. I'm going to go over it both ways. Okay, so I'm first going to use Dr. Planck's notation with his arrow boxes. So we have, initially we have A, and we have B, and we have C. Okay? And he assigns 22, right here he assigns 22 to A. Then he assigns the address of A to C, which means that he makes C point to A. Then we use the dereferencing operator here. So remember, star C means take the value of the variable that C points to. So C points to A, and it says assign the value of that variable, or return the value of that variable. So it returns the value of that variable, and it's 22. Now that does not set up any linkage between A and B. Okay? It is as though, okay, just as if I had said B, well, let's go on. You'll see this in a moment. So we now go to this statement and say A plus equals 10. So A becomes 22 plus 10, it becomes 32. And you'll notice B does not change. Okay, B retains its value of 22. Okay, because this assignment here doesn't set up any linkage between A and B. It is as though this statement had said B equals A. And if I'd done it that way and said A plus equals 10, I don't think any of you would have assigned 32 to B. Okay, that's kind of why we also say that C is an alias for A in this case. Okay, so when I print things out, this prints out 32, this prints out 22, and since this is an asterisk C, it's saying print out the value of the variable to which C points. C points to A, so this prints 32, 22, and this prints 32. Okay, before I take questions, I'm going to show it also the way it's done in memory. So in memory, the way this might be laid out, you might have put A, B, and C here, and we'll put 0x 1,000, and I'm going to dispense with the x's. So these are memory addresses. Okay, so now when I say A equals 22, we put 22 into A. Now when we say C equals the address of A, we put 0x 1,000 into C. Now when we say B equals the dereference of C, we go to the memory address that C points to. So it's 0x 1,000. At 0x 1,000, we see that that location is 22. And we retrieve that value and put it in B. Okay, and finally, we say A plus equals 10, so A becomes 32. Okay, one of my favorite ways to think of a pointer is think of a locker system like at your high school or at a health club. Okay, a locker stores objects or an object, right? And you're given, each locker has a number on it. That number is an address. So you get a key and it has the address 10 on it. So when you go to retrieve the object, you go to locker 10, you open it up, and you get the object out of the locker. So that's the way I like to think of pointers. It's like the number on a locker. So when you say, give me the kind of dereference C, it's like, okay, C has the address of a locker. It happens to be locker 1000. So it's saying, go to locker 1000 and give me the value in that locker. Well, the value in that locker is 32. So that's the way I often like to think about pointers. Kind of like they're the address of a locker When you ask for the dereferenced value of a pointer, you figure out what's the locker it's pointing to. You go to that locker and retrieve the value. Okay, so questions about this first part? You sure? I know this isn't trivial stuff. We're good? Okay. So then moving on to the second part, I posed the question at the beginning, how does a vector actually get access to additional memory? The way that a vector is able to get access to additional memory, and the way you can get access to new memory, is through an operator called new. Okay, so if I say int x equals new int, what happens is that new goes out and allocates 4 bytes, which is the size of an integer, and it returns the address. So what does new do? New finds enough memory, I'll call it free memory, to accommodate or to store an int. So in this case it needs 4 bytes. To new returns the address of this, I'll say, block of memory. Now, where does this free memory come from? So you've already heard of the stack. The stack is where, when you call a function, the compiler creates a stack frame. Well, not the compiler, but the runtime system creates a stack frame, and it stores the local variables. There is another entity called the heap. Okay, and it's where free memory exists. Okay, so a heap contains free memory which new can use to allocate blocks of memory. Okay, and this is happening at runtime. So when we allocate memory from the heap, that's always being done at runtime as the program is running. Okay, and the way that things work, you may have seen this in 160 if you took 160, is when your program starts running, your program is assigned a block of memory in the computer. It's often called the process space. Okay, it may have been called something else in 160, but it's a chunk of memory. So part of that stores your program code. So part of it is your object code. Okay? Part of it is where constants and global variables are stored. Okay, then there is the stack, which works its way up. The heap is at kind of the top of your process space, and it works its way down. Okay? And you may say, well, where's the boundary between the two? There's no real boundary. Initially, kind of conceptually, the stack starts with the creation of main. And initially, nothing's been allocated off the heap, so it's simply the free memory pointer is there. And as new allocates stuff off of the heap, what it's doing is it keeps incrementing this free memory pointer, and it keeps moving down. Okay, now we haven't gotten to delete yet, because you can also delete memory and create holes in this heap. Or not holes, but you can return memory to it. But basically the stack goes up and the heap comes down. Okay, it is possible for your process to run out of memory. If you get into an infinite recursion, then the stack will eventually try to invade the heap, and your program would terminate with a stack overflow error. So if you got into an infinite recursion, most likely you would find your program eventually terminating due to a stack overflow error, and that's because the stack would have grown into the heap. Similarly, if you ask for too much memory, if you keep asking new, eventually the heap may come down and try to encroach on the stack, in which case new will fail. So new doesn't have to succeed. New can fail. If it does fail, it returns a special constant called null, uppercase N-U-L-L. We call it the null pointer. Points to nothing. So new can fail. If new fails, it means there wasn't a piece of free memory large enough to allocate your requested chunk of memory. Okay, that can happen because either the heap has grown so big that it's about to invade the stack, or there's simply, if you look inside the heap, there's free memory, but none of it is big enough to accommodate this block of memory that you're allocating. Okay? Is this clear or makes some amount of sense? I'm just curious, is this covered in 160 or not?
Not the heat.
Not?
We had it last class.
You seen you did?
Yeah, we had it.
You did.
On 60 this semester, we had it.
Kind of. But Gerald, you're saying not in.
When I took last semester, we talked about the stack. We didn't really talk.
Okay, so we kind of have some people who, I'm just curious how much background you might get in 160. Okay, so the heap's going down, the stack's coming up. You can run out of memory in either one. It's much more likely to run out of memory in the heap. Now, in today's memories, you have so much memory, it's actually rather unlikely you would run out of memory, but it is possible. Okay? So back to here, when we say x equals new int, what happens is new is going to the heap. So maybe your process space, say your process space, this would be actually quite small, but let's say your object code starts at 0x0, which it does not. It turns out the operating system code starts at 0x0. So in a real computer, there's a certain amount of code that belongs to the operating system, and that's really what goes at 0x0. But conceptually, we can think of your memory as starting at 0x0. Maybe the stack starts at 0x1000. Maybe your memory goes up to, remember, memories are very big, so we'll say 1 billion. Okay, so it may well be that the first memory space, great, I can't even really figure out, it's going to be, I don't want it to be that big. I'm just going to make it go up to 2,000 so that I can process it a little more easily. Okay, so when you get your first piece of memory, it's 4 bytes. What do you think that memory would be? Can someone do the hexadecimal conversion? If I say x equals new int and it's coming from the top of your process space, what's it going to be? That is very good. 1 FFB. Okay? I believe it is. So if you add 4, B plus 4 is, B is, wait, is it C or A is 10, B is 11. I think it's actually C. C is 12. Okay, so C is 12 plus 4 is 16. So that's 0. Carry the 1. 15 plus 1 is 16. Carry the 1. 15 plus 16, 15 plus 1 is 16. Carry the 1, you get 2. So it's 1 FFC. So you get the memory address you would get would be 1 FFC. And that's big enough to accommodate 4 bytes. So if, remember we had int star x equals new int. So x is down here at location 1000. So here's x down here at location, and it gets 0, it gets 0x1 FFC. In fact, I'm going to, so I get more space so that you can more easily see it. Here is x. It gets 0x1 FFC. Okay, that's part of main. So x is now got the memory address up here. Okay, so it points to this block of memory right here. Okay, same thing. If I now say star x equals 20, what happens is it says, okay, go to the memory address, go to the locker 1FFC, which is up here, and put 20 into it. Okay, so it puts 20 into there. Okay, let's say I have int y. So y is right here, 0x1004. If I now say y equals star x, I'm going to, it says go to the piece of memory to which x points. Well, x points to 1 FFC. Go to that locker and return the value, which is 20, and y gets 20. Okay. Makes sense? So I'm getting new memory off of the heap. What do you think happens if I try to say y equals x? What happens in that case? I'm going to get an address. I'm going to get an error message from the compiler, because the compiler is going to say you're trying to assign an address, because x, when done like that, is an address. Without the asterisk in front of it, you get the address, and it's going to say you're trying to assign an address to an int. And it will tell you it's an error. It will say incompatible types. Okay, watch. We even do that. Create a quick program. So we'll create an int star x. We'll create int y. We'll try to say y equals x. Okay, very simple, right? And there's the program. Whoops. Let's compile that puppy. See, error. Assigning to int from incompatible type D type int star. Then the next thing is a suggestion. It says dereference with star. So it's trying to suggest how you might fix the error. Okay, which is to assign which is to put an asterisk in front of the x. Okay, yes.
Is this the same error message that would be generated on like Hydra? Because that looks so nice and pretty.
Let's try it. The answer may be no. So let's copy that. Here show the Hydra. I didn't get the password right. It's going to so if it's ever slow like this, W, wow, the load average is 10. That's why it's so friggin' slow. So
What does load average mean?
it's kind of a measure of how heavily loaded the machine is. When I was, it's something below 1 means it's lightly loaded. I don't even anymore know. I remember back in the day when I started, load average was like roughly 1 person on the machine. So this is like there's 10.5 people wailing on the machine. But you can think informally like that. You see there's not that many people, but a program can hog the CPU. So it's slow because something's hogging the CPU. Okay? So at any rate, let's just try it. Oh, no, we're not. We're going to exit and try another Hydra machine. It's always good to go up to a higher one because people don't seem to use the higher ones as much. Ah, much better load average. Okay. Okay, there's my program on Hydra. Oh, wow, you're right. Not nearly as nice. Error, invalid conversion from int star to int. Yep, not nearly as nice of an error message.
Isn't the compiler on Hydra an older version?
So the compiler, it's not so much that. So the compiler on Hydra is the GNU compiler. On the Macintosh, it's a compiler actually called Clang, which is developed at the University of Illinois. Now, when you type G++ on the Mac, it's aliased to the Clang compiler. So you think you're invoking the GNU compiler, but in fact, you're invoking Clang. So in fact, there are two different. The one on the Mac is Clang, and it's producing better error messages. Okay. So yes, on Hydra, it won't be as nice. Okay. While we're at it, there are some things that you should also now, I need to talk a little bit about. First of all, it becomes a lot worse when you fail to initialize pointers. A lot worse. Okay? So let's just see here. I completely forgot to initialize x, right? See that? X doesn't. So let's actually try to assign y the value of x. I haven't initialized x, right? Do we agree? So we don't know what x contains. Okay, whoops, gotta turn it into an executable. So let's run it. Whoops. F stands for finger. So it tells me who's on this machine. Oh, foo. Try foo. What? Shouldn't be working. Wow. Let's print Y. It must be printing to, actually I'm going to try something. We're going to print out the value of x and the value of y. Okay, so let's see what's going on. Do we see that program? Okay, actually, just a second. So that you can see the program, and see my compilation, I'm going back to the Mac. Okay. So here's the program. How do we, Alan told you how to do this, how do we make it nicely indented? How? Someone say it. 1 lowercase g equal capital G. Whoops, that didn't work because, what is it? What is it, Alan? 1 capital G equal what? Wait. Okay. 1 capital G equal capital G. So 1 capital G equals capital G is the sequence. Okay, whoops. I can, but that was what Alan put on Piazza, so that's just. Okay, so there's our program, correct? Getting off of Hydra now. So O foo f.cpp error y, because I didn't save it. Okay, let's run it. Segmentation fault, that's more like it. Okay, something that is near and dear to your hearts. Why do you get segmentation faults up to now? What was the reason that you got segmentation faults in your labs?
Messing with memory you're not allowed to.
You're accessing memory that you weren't allowed to, but what was the specific cause? Because there was generally only one thing you were doing that was, you're going outside a vector, outside the range of the vector. So you were accessing memory that you're not allowed to access. So a segmentation fault occurs when you try to access memory that you're not entitled to access. So there's a lot of protected parts of memory. For example, the operating system. You're not allowed to go into the operating system's memory for good reason. Okay? If I was allowed to go into the operating system, it would be a hacker's dream scenario. They could go in and alter the operating system. Okay, you can't get into your code and alter it, or you're not supposed to be able to get into your code and alter it. So if you try to get into a piece of memory where your code is stored, that will be a segmentation fault. Okay, so pointers come up with the real chance that it's a segmentation fault. So what probably happened here? Well, what most likely happened is right here. When I tried to access X, it contained an invalid address. Okay, a good possibility, well, we can see, we'll put the, let's move the cout statement above there so we can see what X actually points to before it goes into its dump. Okay, what does X point to? 0. Okay, if we look back here, well, it's either, this is where I'm not a systems person, you're either trying to get at absolute 0 memory, which is where the operating system is, or you're trying to get at your object code. In either event, 0x0 is considered an invalid piece of memory. Okay? And it causes a segmentation fault when you try to access that piece of memory. Just for grins, let's see what null is equal to. Because I said that's what gets returned. Null is undefined. I think it's C standard lib is going to have null. Nope. This isn't good. Pardon? What do you think? You're not, oh, I'm not compiling the right? No, I'm compiling the right. Oh, wow. Of course. Thank you. Thank you so much. Okay. Leave that out. Compile it over here. This is what happens when you, there we go. So null is also equal to 0. Okay? Now, you're saying, okay, the memory, if I don't initialize, is assigned to 0. No, 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 not necessarily. It could be anything. The point is that if you don't initialize a pointer's memory, it can be anything. Okay? I was just showing you that null is actually 0. That's what it's defined to be. But you're going to have to get used to segmentation faults because pointers really introduce this in spades, this kind of pointer issue, or this segmentation fault issue. Okay? So, questions? Because I know we've been covering a bunch of stuff.
On that segmentation fault error, that number after it, what significance is that?
No real significance. It's some kind of message, I believe, Alan, you might also know, I believe it's a signal when a program is able to have certain what are called signals, and I believe 11 is a signal for a segmentation fault. I'm not 100% positive. You might know. Right. I think 11 is the so-called signal that's sent on a segmentation fault. There's other kinds of faults. You might see a fault called a bus error, okay, which is much less common than a segmentation fault. When I was going through school, there were certain addresses. So you saw that an int is 4 bytes, right? So an int should always be stored in an address divisible by 4. So when I at least was going to school, if you tried to say int star x equals, say, 0x1001, and you tried to do an access through it, you didn't get a segmentation fault, you got what was called a bus error. And the reason was it was a unaligned memory address because all integer addresses were supposed to be divisible by 4, and this one wasn't. Now, it seems like that's not always the case anymore. Now, sometimes, or oftentimes when I do this, I still get a segmentation fault. But I do know you may also see bus error. That's another kind of error. It also means you have an issue with your pointer. One possible issue is that the address is not divisible by the right number. So what it's saying often with a bus error is that the type of memory you're trying to access, in this case an integer, could not possibly start at that address because it can't possibly start at an address not divisible by 4. So you may also start to see bus error as a reason for your program terminating. It also means you have a problem with your pointer. Okay. Other questions? Okay, so I'm just going to now quickly show you, segue to Dr. Planck's, not this, you'll do this in one moment, so that'll be the last thing you do. Okay, so he had his thing. Okay, so here's his start of stuff. So he declares an int I and 2 pointers, IP1 and IP2, for integer pointer 1 and integer pointer 2. You see that he gives IP the address of I, so he's making, nice. Okay, that's a slight bug. He should have said, this should be, I'll fix it. This should be IP1. So he's making IP1 point to I, and then he's assigning I5. Then, whoops, he's asking new for a new block of memory, and it gives him a new block, and he makes IP1 point to that new block. And you see that IP1 no longer points to I. So now when we assign 10 to the dereferenced IP1, it's saying assign 10 to the so-called locker that IP1 points to. Well, it points to this locker, so it stores 10 into there. Now, we're continuing to execute code. We again ask new for an int, and it gives us a new one right here, so IP1 points to here. And we assign 15 to it, so it's now 15 is in that locker. And you'll see that nothing points to 10. Okay? This is what we call a memory leak. It is impossible to get back to this particular piece of memory. We've lost any access to it. Now you may say, what about I? I can still get at I by saying I. Okay, this one right here is on the stack, but this one and this one is on the heap. Both of those are on the heap. We lost the pointer to 10. It's a memory leak. It's like you lost the key to a locker. It's gone. Okay? There's something that you have to do to reclaim memory. But we haven't got to that yet, so don't worry about it. Just know that you'll hear the term memory leak, and it can be an issue. Okay? Now we set IP2 equals to IP1. Okay? So we assign the memory address in IP1. So if IP1 had been 0x, say, 1FFC, now IP2 will also be 0xFFC. So they'll both point to the same piece of memory. And if we assign 20 to the dereferenced IP2, it changes that memory. So you can see now that we have 2 pointers to the same piece of memory. And if we print out either IP1 or IP2, we would get, so if we print it, this is just pseudocode, star IP1, it would actually print 20, because that's the value of the memory to which it points. Okay? Questions? Well, if not, then I want you to try it yourself. So, tackle the second part of Dr. Planck's question. Again, I'll give you about 5 minutes for this, and with about 2 minutes to go, I'm going to go over the solution. So again, if you have questions, please ask. Feel free to work on it with a neighbor. Have you ever encountered crosshair?
Someone just asked.
Someone raise their hand.
Someone just asking if you could scroll.
Did,
Or
oh, the variable declaration, sorry.
sorry, what was you asking? Just something on like the select how architecture and very hard to say similar
I'll have to see again.
in binary on the wrong architecture, all kinds of
Usually when I try it, I just get error messages that says, this is the wrong architecture. Oh, I see. You're right. Yeah.
By the way, I think Dr. Pott told this one time in the past that the first addresses are invalid, not because they're OS codes, because it's just a cache, because bad pointers are often 0 or some low value, you factually assign a link to the pointers. That can be just as an index, it's like false.
Makes sense. Either when you say 0, but that is an absolute very interesting process as opposed to. I thought it was 2 that it was so exactly. So in any event, lower addresses are deep reference but if it was like 0 or whatever 1,000 is, it gives me a 1. So, so what it prints for this is release that part.
Just as you're asking to print whatever it is,
Oh, okay.
And then that value is going to be, if you dereference it, it's going to interpret it as goes that way.
I know. You likely have a memory issue. I've seen that happen in my code too, where putting in or taking out, usually what's happening is it's shifting your memory enough that it works. I'll take a look.
It's going to be some random. It's saying interpret that random number as an
Right, so it's so I'll take a look at it in just a moment. Okay, y'all, we got about 2 minutes, so I just want to show you what is going on. Again, both with Dr. Planck's notation and then the way the machine stores it. So again, we have A, B, C, and D in Dr. Planck's notation. When we say C equals new int, we're getting, could we pipe down please? I'm hearing chatter, so. When we say C equals new int, new assigns, allocates a new block of memory and gives it to the address to C. So C points to that new unnamed memory. Okay, there's no name for it. When we say now star C equals 88, 88 gets assigned to what C points to. Now we say D equals C, and you can see D is a pointer, so D now also points to that piece of memory. Now we say A equals the contents or the value of the memory to which C points. C points to the value 88, so A gets assigned 88. Now we say star C equals 77. So it says go to the memory to which C points and assign it the value 77. So now this becomes 77. Okay? Now it says B equals A, so that's easy enough. B is just an int. And B equals B plus 5. So B is 93. So when we print A, that prints 88. When we print B, that prints 93. When we print star C, we print the value of memory to which C points, that's 77. And when we print star D, it's also the memory to which D points. Okay, hold on. Let me just quickly do it the other way, just so that you can see the other way. So the other way, we have on the stack A, B, C, and D. Okay, when we assign this C, when we say new int, then let's say this is 0x2000. So 0x2000 gets stored in C. Then star C equals 88, so we go to 0x2000. So in effect, remember we say it's off the heap, so what's really happening is this is your entire process space. So way up here we're saying is 0x2000, so we had 88, we're putting 88 into that space. Now we say D equals C, so that becomes 0x2000 because it gets the memory at the address that C stores. Then A equals the value of memory to which C points. Well, C has the memory address 2000, so when we go up to 2000, we see it has 88. So A gets 88. Now, the memory that C points to, well, that's 0x2000. It points to 0x2000, gets 77. Okay, that's what this statement does. Then B equals A, and B equals A plus 5. Same thing. It's just that's the way in green it actually happens in the real memory. In blue, that's kind of the conceptual way you can think of it. Either way is fine, as long as you get to the right answer. Okay? So again, remember, Thursday exam, try to be prompt, and good luck with the exam on Thursday.